welcome to the first lesson of AS Physics online crash course. Students, before we start the lesson, let me give you a quick introduction to the AS Physics syllabus and papers. Students, altogether there are 13 chapters in the AS Physics syllabus, and I plan to cover all of them in 50 lessons of total time duration about 20 hours. Students, each lesson will consist of two parts. In the first part, we will learn 1, 2, or 3 topics of AS Physics in about 10 to 12 minutes, depending on the size of the topics, of course. And in the second part, we will do past paper questions on the topics covered in the first part of the lesson. And then at the end of each lesson, I'll give you some more past paper questions for practice that you have to do in your AS Physics workbook of topically arranged past paper questions. Students, you can download the printable PDF file of the workbook by clicking the link given in the description below. The file name is AS Physics P2 Unsolved. Students, this workbook contains past paper questions of almost all styles. And I'm sure after finishing this workbook, you'll be able to do about 90% questions of any AS Physics paper you pick. Students, note that there are actually 2 links given in the description below. One for my AS Physics workbook with file name AS Physics P2 Unsolved, and one for my AS Physics notes with file name AS Physics P2 Solved. Students, these notes cover 100% syllabus. They contain all definitions, all statements, conditions, derivations, explanation, formulas, and equations included in our official AS Physics syllabus. And not only that, they also contain solutions to all past paper questions of the workbook along with explanation. Let me show you the front titles of my AS Physics workbook and notes now. See students, this is the front title of my AS Physics workbook of topically arranged unsolved past paper questions of almost all styles. And this is the front title of my AS Physics notes. They cover 100% syllabus and also contain solutions to all workbook questions along with explanation. So students, to make the most of this online course, watch the lesson first, then read the topics covered in the lesson from my notes. Learn all the definitions, statements, formulas, and equations, and then do the workbook questions in the same order as given in the notes at the end of each topic. Actually, students, in my notes, the solved questions have been arranged in the increasing difficulty level order. So when you do the workbook questions, try to follow the same order as given in the notes. However, if you get stuck on any question or on any part of a question, you can always get help from the notes. Like I just said, that the notes contain solutions to all workbook questions along with explanation. Let's look at AS Physics papers now. Students, in AS, all physics students take 3 papers. Paper 1, Paper 2, and Paper 3. Students, Paper 1 is an MCQ paper of 40 marks. This paper consists of 40 MCQs. Paper 2 is a theory paper of 60 marks. Students, this paper usually consists of 6 or 7 structured questions. And paper 3 is an advanced practical skills paper of 40 marks. Students, this paper consists of 2 questions and each question requires practical performance of an experiment. So in this online course, we will only cover paper 1 and paper 2 and not paper 3 because this paper requires practical performance of experiments. Students, of all 3 papers of AS Physics, paper 2 is the most important paper because this paper contributes 46% towards your overall grade in AS Physics. The second most important paper is paper 1, the MCQ paper. It contributes 31% towards your overall grade in AS Physics. And the least important and also the easiest paper is paper 3, the advanced practical skills paper. Students, this paper contributes only 23% towards your overall AS Physics grade. Now, speaking of grades, students, there is a very important concept of grade threshold that you should all know about. See students, paper 1 is an MCQ paper of 40 marks and 80% of 40 is 32, right? Now, mostly A-level physics students believe that to get an A in this paper, they need to score at least 32 marks in it. But this is not true. Actually, students, you need to score only about 29 marks on average in paper 1 to get an A in it, where 29 is the average grade threshold for an A grade in paper 1 over the past 20 years. That is, 29 is the average of all grade thresholds for an A grade in paper 1 over the past 20 years. But students, note that you cannot always get an A in paper 1 by scoring about 29 marks in it, because the grade threshold for a given grade in a paper actually depends on the difficulty level of the paper. So when the difficulty level goes up, the grade threshold goes down, and similarly when the difficulty level goes down, the grade threshold goes up. Students, you might find it surprising that in the past 20 years, the lowest grade threshold for an A grade in paper 1 has been just 25 and highest 35. 25 was the grade threshold for an A grade in paper 1 in October number 2014 and 35 in October number 2006. Let's look at paper 2 now. Students, paper 2 is a theory paper of 60 marks and 80% of 60 is 48. But here again, to get an A in this paper, you don't need to score 48 marks or above that. Rather, you need to score only about 38 marks on average in paper 2 to get an A in it. Because in paper 2, 38 is the average grade threshold for an A grade over the past 20 years. Now, just like paper 1, the grade threshold for a given grade in paper 2 is also not fixed. It also varies with the difficulty level of the paper. It is low for a difficult paper and high for a relatively easy paper. For example, in the past 20 years, the lowest grade threshold for an A grade in paper 2 has been 30, which is just 50% of the total marks. And the highest grade threshold for an A grade in paper 2 has been 48. Students, 30 was the grade threshold for an A grade in paper 2 in October number 2015 and 48 in February-March 2020. Students, note that in paper 2, the average grade threshold for an A grade is very low, 38, which is just 63% of the total marks, right? So this low grade threshold for an A grade in paper 2 suggests that perhaps getting an A in paper 2 is very easy, because see, you can lose out of total 60 marks in paper 2, about 22 marks and still expect to get an A in it. So securing an A in paper 2 seems very easy, but students, trust me, it's not. Let me explain why. Actually, students, sometimes it's very easy to lose marks in paper 2. For example, a lot of students lose marks in paper 2 just by omitting the keywords from their statements and definitions. Let me give an example here. Students, sometimes in paper 2, we are asked to state the principle of momentum conservation. And this part of the question is usually for 2 marks. Now, to score full marks in this part, we should write this statement as our answer. The total momentum of an isolated system remains constant. Now see students, this statement has 2 parts. We are awarded an M mark for the first part that says the total momentum remains constant, and an A mark for the second part that says of an isolated system. Now students, note that if we omit just one word, total, from the first part of the statement, we will lose both marks, M and A, and end up getting a 0. Let me explain why. Actually, students, total is the keyword in the first part of the statement. So if we omit it, we will lose the M mark. And as for the A mark, according to the marking rules specified by the CIE, Cambridge International Examinations, it depends on the M mark. And if a candidate fails to score an M mark in a part of a question, he loses all the A marks of that part too. So here, as you can see, omitting just one word, total, from the statement of principle of momentum conservation costs us 2 marks, and we end up getting a 0. So students, remember, when you learn the definition of a physical quantity or the statement of a law, always pay particular attention to the keywords, remember them and never omit them. To make this easier for you, in my notes, the keywords in all the definitions and statements have been underlined, so you can easily identify them when you learn the definitions and statements. Now, other silly mistakes that students make in paper 2 include not showing working when it's required. For example, not writing the formula used for calculation. I don't understand why students do that. It takes less than 2 or 3 seconds to write a formula or an equation. So students, always write the formula when you're asked to show your working as well. Another very common silly mistake that students make in paper 2 is doing the calculation without converting the units first. For example, from centimeter to meter, and then finally stating the answer to less than the required number of significant figures. Students, over the years, I have seen many smart kids make these mistakes and lose marks. So if you want to secure a decent grade in A-level physics, avoid these mistakes. And lastly, students, remember that learning a topic in A-level physics is one thing, and being able to do exam style questions on that topic is a whole nother story. So in this online course, I'll teach you all the important tips and tricks that will enable you to do exam questions of almost all styles. We will learn some of these tips and tricks in this lesson too. There's a lot to learn. So without further ado, let's start our first lesson now. The first chapter in the AS Physics syllabus is physical quantities and units. Students, this chapter is the easiest chapter in the whole syllabus. It's also an important chapter from the examination point of view because see, the first 2 or 3 MCQs of paper 1 are always from this chapter. So we can say that this chapter contributes on average about 7% to paper 1, the MCQ paper. As for paper 2, the theory paper, the average contribution of this chapter to paper 2 is also about 7%. Now students, all together, there are 9 topics in this chapter, and in this lesson, we will learn the first 3 topics. The first topic is SI-based quantities and their units. The second topic is determining the SI-based units of derived quantities. And the third topic is checking the homogeneity of physical equations. Let's start with the first topic, SI-based quantities and their units. Students, we learned in the IGCSE that physical quantity is a property or a feature that can be measured and then expressed using a numerical magnitude and a unit. For example, let's say we have a block and the mass of the block is measured to be 500 grams. Now here, mass is a physical quantity and 500 gram is the value of mass. And in the value of mass, 500 is the numerical magnitude and gram is the unit. Students, remember that all physical quantities consist of a numerical magnitude and a unit. So if there is a property or a feature that can be measured but does not have a unit, then it cannot be regarded as a physical quantity. Take efficiency for instance. The efficiency is given by the expression output power over input power times 100. Now, from the expression for efficiency, it follows that it has no units because the units of output power and input power cancel out, leaving no units for efficiency. So technically, efficiency is not a physical quantity. Now look over here. Students, SI-based quantities are the quantities that form basis for all other quantities. That is, all other quantities may be expressed in terms of these quantities. Take speed for instance. We know that speed is given by the expression distance covered over time taken. Now here, distance and time are both base quantities. And speed on the other hand is a derived quantity. because it is expressed in terms of two base quantities. Students, in the international system of units, which is also known as SI, 7 quantities have been chosen as the base quantities. But out of these 7 base quantities, only 5 are included in our AS physics syllabus, and you have to memorize their names as well as units, which are length, unit meter, mass, unit kilogram, time, unit second, current, unit ampere denoted by capital A, and temperature, unit Kelvin denoted by capital K. Students, these are the 5 base quantities included in the AS physics syllabus, and these are their units. They are also known as SI base units. Students, you have to memorize the names of these base quantities as well as their units. The next topic is determining the SI base units of derived quantities. Students, derived quantities are those quantities that may be expressed in terms of base quantities. Actually, students, all quantities other than base quantities are derived quantities. For example, speed, acceleration, force, pressure, they are all derived quantities. Now, let's learn how to determine the SI base units of derived quantities by doing a sample question. The question says, determine the SI base units of pressure. Students, we know that the SI unit of pressure is Pascal, but here we have been asked to determine the SI base units of pressure. Now students, listen very carefully what I am going to say next, because this is the key concept in this topic. To determine the SI base units of any quantity, all we need is the expression for that quantity. Now, to determine the SI base units of pressure, all we need is the expression for pressure. Students, we know that pressure is given by the expression F over A, where F is force and A is area. Students, the SI unit of force is Newton and SI unit of area is meter squared. Students, note that meter is an SI base unit, but Newton is not an SI base unit. Remember what I told you in the previous slide, that there are only 5 SI base units that we have to deal with in AS: meter, kilogram, second, ampere, and Kelvin. And see, Newton is not one of them. So now, to be able to determine the SI base units of pressure, we have to determine the SI base units of force first. Now look, the key concept says to determine the SI base units of any quantity, all we need is the expression for that quantity. So to determine the SI base units of force, all we need is the expression for force. Students, we know that F is equal to ma, where m is mass and a is acceleration. Let's now replace F by its expression ma to obtain a new expression for pressure. Students, in this new expression for pressure, m is mass, the SI unit of mass is kilogram, which is also an SI base unit. A is acceleration, the SI unit of acceleration is meter per second squared, where meter and second are both SI base units, and capital A is area, the SI unit of area is meter squared, where meter is again an SI base unit. See students, we have finally obtained an expression for pressure in terms of quantities we know the SI base units of. Now let's use this expression to determine the SI base units of pressure. So SI base units of pressure are equal to SI base unit of mass, which is kg, times SI base units of acceleration, which are meter per second squared, over SI base unit of area, which is meter squared. Students, let's simplify this expression now. See, this meter in the numerator and 1 meter in the denominator cancel out, leaving 1 meter in the denominator. When this meter is shifted to the numerator, it becomes meter inverse. And so the whole expression simplifies to kilogram per second squared per meter. which are the SI base units of pressure. See students, we determined the SI base units of pressure by using the general expression for pressure, P equal F over A. Students, if we had used a different expression for pressure, let's say if we had used this expression, P equal rho GH, where rho is density, G is acceleration of free fall, and H is depth, it would also have produced the same result because the choice of expression does not make any difference here. Just remember that to determine the SI based units of a quantity, we start with a valid expression for the quantity. Then we get rid of those quantities in the expression we don't know the SI based units of. We get rid of those quantities by replacing them with their expressions, and we keep doing that until we obtain a final expression for the quantity in terms of quantities we know the SI base units of. Then we replace those quantities by their SI base units, and finally we simplify that expression of SI base units to obtain the SI base units of the quantity. The next topic is checking the homogeneity of physical equations. Students, look at this sample equation first. AB plus C over D is equal to E squared. Students, look, this equation has three terms, AB, C over D, and E squared. Now, a homogeneous equation is the one in which all terms have the same SI base units. And students, remember that only a homogeneous equation may be correct, because all correct equations are always homogeneous. On the other hand, a non-homogeneous equation is the one in which different terms have different SI base units. Students, note that a non-homogeneous equation is always incorrect. So if you come across a non-homogeneous equation, straight away reject it. Now let's do an example to learn how to check the homogeneity of physical equations. Let's say there is a car and it's moving along a straight road. At time t equal to 0, its initial velocity is u. The car starts accelerating at time t equal to 0 with constant acceleration a, and in time t, it covers distance s in the direction of motion. Now let's say student A suggests that the quantities s, u, a, and t are related by the equation s equal ut squared plus half at. Now students, if this equation is correct, then it must be homogeneous. So let's check the homogeneity of this equation now. Students, first of all, note that this equation has three terms, s, ut squared, and half at. Now if all the terms have the same SI base units, then the equation is homogeneous and may be correct. But if the terms have different SI base units, then the equation is non-homogeneous and must be incorrect. So let's calculate SI base units of each term now. SI base units of the first term S, SI base units of the second term ut squared, and SI base units of the third term half at. Students, SI base unit of the first term S, which is distance, is meter. SI base units of the second term ut squared are equal to SI base units of initial velocity u, which are meter per second, times SI base unit of t squared, which is second squared. Let's simplify this expression now. Second inverse times second squared is equal to second. So the whole expression simplifies to meter second. So meter second are the SI base units of the second term. Let's calculate SI base units of the third term now. Students, note that in the third term, 1 over 2 is a coefficient, and coefficients have no units. So SI base units of the third term half at are equal to SI base units of acceleration a, which are meter per second squared, times SI base unit of time t, which is second. Let's simplify this expression now. Inverse of second squared times second is second inverse. So the whole expression simplifies to meter per second. So meter per second are the SI base units of the third term half at. Students, note that different terms in the equation suggested by student A have different SI base units. So the equation is non-homogeneous and must be incorrect. It will never hold true. It's just like saying that 2 apples plus 3 oranges is equal to 5 mangoes, which is bananas. Totally absurd, because you cannot add, subtract, or equate things that are different by nature. And similarly in physics, you cannot add, subtract, or equate physical quantities that have different SI base units. Now let's say another student B, suggests a different equation. S equal UT plus half AT squared to relate S, U, T and A. Students, this equation also has 3 terms, S, UT and half AT squared. To check the homogeneity of this equation, let's calculate SI base units of each term in the equation. SI base units of the first term S, SI base units of the second term UT, and SI base units of the third term half AT squared. Students, SI base unit of the first term S is meter. SI base units of the second term UT are equal to SI base units of initial velocity U, which are meter per second, times SI base unit of time, which is second. Let's simplify this expression now. Second inverse and second cancel out, and the whole expression simplifies to meter. So meter is the SI base unit of the second term too. Let's calculate the SI base units of the third term now. The SI base units of the third term are equal to SI base units of acceleration A, which are meter per second squared, times SI unit of t squared, which is second squared. Let's simplify this expression now. Inverse of second squared and second squared cancel out, and the expression reduces to meter. So meter is the SI base unit of the third term too. Now students, note that all 3 terms in the equation suggested by student B have the same SI base unit, meter, so the equation is homogeneous and may be correct. Students, the third topic, checking the homogeneity of physical equations, ends here. Now let's do some past paper questions on all the 3 topics learned in this lesson. Before we do the past paper questions, let me tell you some very important things about the structure and format of paper 2 and its questions that you should all know about, because the knowledge of these things will help you budget your time wisely in paper 2. So the first thing you should know about paper 2 is that it usually consists of 7 questions, and you have to do all 7 of them in 1 hour and 15 minutes. Each question has several parts, and some parts even have subparts. Students, the first part in almost all 7 questions of paper 2 is the easiest part, because in this part we are usually asked to define a physical quantity, or to state a law, or to state the meaning of a term used in physics, or to describe a phenomenon, etc. The next part is a little bit difficult than the first part. Students, in this part, we usually have to use a direct formula to calculate the value of an unknown quantity. The next part is even more difficult. So students, see, as we proceed within the same question in paper 2, the difficulty level keeps increasing, which means that the last part of almost all 7 questions of paper 2 is the hardest part. Students, in this part, we are usually asked to sketch a graph, or to state and explain change in something, or to comment on something, or to suggest something, etc. Almost all students find the last parts of paper 2 questions relatively difficult. But a good thing about the last part of any paper 2 question is that it's usually for 1 or 2 marks only. So even if you get all last parts wrong, you will only lose 10 to 12 marks, which means that you will still have 10 to 12 more marks to lose before you lose your chance of getting an A in paper 2. Remember, I told you in the introduction that in paper 2, the average grade threshold for an A grade is about 38, which means that You can lose out of total 60 marks in paper 2, about 22 marks and still expect to get an A in it. So my first tip is that in the exam, focus more on the initial parts of paper 2 questions because they involve calculations and it's relatively easy to score full marks in these parts. And don't linger over any last parts you can't figure out. It's not worth it. Instead, skip to the next question because the time is extremely tight in the exam. Another important thing about the structure of paper 2 questions is that when doing a part of a paper 2 question, say second part, we often use our answer to the first part. And similarly, when doing the third part, we often use our answer to the second part. Now let's keep these things in mind and do some past paper questions on the 3 topics covered in this lesson. Let's start with question number 3 of chapter 1 in the workbook. Question 3 part A subpart 1 says define power. Students, we know that power is given by the expression W over T, where W is work and T is time. So power may be defined as work done over time taken. Students, note another very useful tip here. You may define a physical quantity by writing its expression using words, but not using symbols. Students, you may also define a physical quantity by writing a statement. For example, you may define power as the rate of doing work or as the work done per unit time. Students, both definitions are right, but I prefer this style of defining a physical quantity by writing its expression using words because it's the easiest and flawless way of defining a physical quantity. On the other hand, when you define a physical quantity by writing a statement, a little mistake in the choice of words loses you marks. For example, if you define power as the work done in a unit time, you will lose the mark here because unlike the above statement, work done per unit time, the statement work done in a unit time fails to express the idea that power is actually equal to work done divided by time. Similarly, students, it would be wrong to define power as the work done per second because second is a unit, not a physical quantity. And by rule, a physical quantity should only be defined in terms of other physical quantities, not units, and a unit should be defined in terms of other units, not physical quantities. For example, look over here. The SI unit of power is watt, the SI unit of work is joule, the SI unit of time is second. So watt may be defined as joule over second. Let's move on to the next part now. The next part says, show that the SI based units of power are kilogram, meter squared per second cubed. Students, note that in this part, the paper setter has already given us the SI based units of power, and he is now asking us to show that the SI based units of power are these. Students, he could have asked us to calculate the SI based units of power, but he didn't. You know why? Because these units are actually to be used in the next part of the question. So note another very important tip here. When in paper 2, you are asked to show that something is equal to this. It means that that something, which may be a value or an equation or a formula, is to be used in the next part of the question. So use the term show that as a hint for the next part. Now let's calculate the SI based units of power. Students, we know that power is given by the expression P equal W over T. The SI unit of work is joule and SI unit of time is second. Students, second is an SI based unit, but joule is not an SI based unit. Remember, I told you that there are only 5 SI based units that we have to deal with in the AS: meter, kilogram, second, ampere, and Kelvin. And joule is not one of them. So let's replace work by its expression, force times displacement, to obtain a new expression for power, which is F times S over T. SI unit of force is Newton, SI unit of displacement is meter, and SI unit of time is second. Students, see, second and meter are SI base units, but Newton is not an SI base unit. So let's replace force by its expression now. We know that force F is equal to ma, where m is mass and a is acceleration. Let's now replace f by its expression and obtain another new expression for power, which is MAS over T. The SI unit of mass is kilogram, which is also an SI base unit. The SI unit of acceleration is meter per second squared, where meter and second are both SI base units. The SI unit of displacement S is meter, which is again an SI base unit. An SI unit of time is second, and second is also an SI base unit. So students, we have finally obtained an expression for power in terms of quantities we know the SI base units of. Now let's use this expression for power to calculate its SI base units. So the SI base units of power are equal to SI base unit of mass, which is kg, times SI base units of acceleration, which are meter per second squared, times SI base unit of displacement, which is meter, over SI base unit of time, which is second. Let's now simplify this expression of SI base units. Students, this second in the denominator when shifted to the numerator becomes second inverse. Now the whole expression simplifies to kilogram meter squared per second cubed, which are the SI base units of power. Students, see, they match the SI base units of power given in the question. Students, note that in this part, we started our solution with the expression for power that we actually used in the previous part. Remember, I told you in the previous slide that when doing a part in a paper 2 question, we often use our answer to the previous part. Let's do the next part now. The next part, part B, says all bodies radiate energy. The power P radiated by a body is given by P equal Ka T to the 4, where T is the thermodynamic temperature of the body, A is the surface area of the body, and K is a constant. Subpart 1 says determine the SI base units of K. Now here students, to determine the SI base units of K, we need this expression, which we can obtain from the given equation. So making K subject of the equation gives K equal P over A times T to the 4. The SI base units of power are kilogram meter squared per second cubed. Students, remember that these are the same SI base units given in the previous part of the question, and now we are using them here in this part. A is area and SI unit of area is meter squared, where meter is also an SI base unit. T is thermodynamic temperature, its unit is Kelvin. So SI unit of T to the 4 should be K to the 4, where K is also an SI base unit. So students, this is the expression for K in terms of quantities we know the SI base units of. So we can simply replace these quantities by their SI base units to determine the SI base units of K. So the SI base units of K are equal to SI base units of power kilogram meter squared per second cubed over SI base unit of area meter squared times SI base unit of T to the 4, which is K to the 4. Meter squared in the numerator and meter squared in the denominator cancel out. This K to the 4 in the denominator when shifted to the numerator becomes K to the minus 4, and hence the whole expression of SI base units reduces to kilogram per second cubed K to the minus 4. Let's do the last part of the question now. The last part says on figure 1.1, sketch the variation with T squared of P. The quantity A remains constant. Students, in this part, we have to plot a graph of P against T squared. Students, first of all, note that every graph is plotted from its own equation. An equation that relates the quantities taken on the y and x axis. So, to be able to plot a graph of P against T squared, we need an equation that relates P and T squared. Fortunately, that equation has been given in the question, in the previous part actually, but we are going to use that equation in this part. P equal Ka T raised to the power 4. Students, in this equation, K and A are both constant. See? So the product of K and A is also constant. So from this equation, we can write P is proportional to T raised to the power 4. Now from this proportional relationship, we can write P is proportional to T squared raised to the power 2. We did this step because we want to plot a graph of P against T squared, not against T raised to the power 4. Students, now stop here and look over here. We learned in the IGCSE that if y is proportional to x, then y versus x graph is straight line and passes through the origin. But if y is proportional to x raised to the power 2, then y versus x graph is not straight line, rather it is parabolic. Now compare these two proportional relationships. Here y is proportional to x raised to the power 2 and here p is proportional to t squared raised to the power 2. So the similarity between these two situations suggests that just like y versus x graph is parabolic, p versus t squared graph should also be parabolic. Students, this is the last part of this question and this is the reason why it's so hard. But you don't have to worry too much about the last parts of paper 2 questions because they usually are just for 1 or 2 marks. Let's do one more past paper question from the workbook now. Let's do question number 14 now. Question 14 part A says use the definition of work done, which we know is force times displacement, to show that SI based units of energy are kilogram meter squared per second squared. Students, we know that work and energy, they both have the same SI unit, joule. So they should also have the same SI base units, which means that we can use the expression for work to show that the SI base units of energy are kilogram meter squared per second squared. So let's start with the expression for work now. W is equal to Fs. The SI unit of force is Newton and the SI unit of displacement is meter. Students, meter is an SI base unit, but Newton is not an SI base unit. So let's replace F by its expression MA. So replacing F by its expression MA gives MAS, where M is mass, its SI base unit is kg, A is acceleration, its SI base units are meter per second squared, and S is displacement, its SI base unit is meter. Now see students, we have obtained an expression for work. In terms of quantities, we know the SI base units of. So let's replace these quantities by their SI base units now and calculate the SI base units of work. So SI base units of work or energy are equal to SI base unit of mass, which is kg, times SI base units of acceleration, which are meter per second squared, times SI base unit of displacement, which is meter. Now students, simplifying this expression gives kilogram meter squared per second squared, which are the SI base units of work or energy, and you can see that they match the SI base units of energy given in the question. Let's do the next part now. Part B says define potential difference. Students, we learned in the IGCSE that potential difference V is given by the formula W over Q, where W is the energy transformed from electrical to other form and Q is the charge. So potential difference may be defined by rewriting this expression using words energy transformed over charge. Let's do the last part now. The last part, part C, says determine the SI base units of resistance and show your working. Students, to determine the SI base units of resistance, we need an expression for resistance. Now students, we learned in the IGCSE that resistance is given by the expression V over I, where V is the potential difference and I is current. The SI unit of potential difference is volt and SI unit of current is ampere. Students, ampere is an SI base unit, but volt is not an SI base unit. So let's replace potential difference by its expression so that we can determine the SI base units of resistance. Now, we just stated in the previous part that potential difference is given by the expression energy transformed over charge. So replacing V by its expression gives W over QI. Students, the SI base units of energy are kilogram meter squared per second squared. Students, these are the SI base units of energy that have been given in part A. Now Q is charge and its SI unit is coulomb, I is current and its SI base unit is ampere. Now see students, coulomb, which is the unit of charge, is not an SI base unit. So we will have to replace charge Q by its expression now. Now look over here. The expression for charge Q may be obtained from the general expression for current, which is Q over T. Now making Q the subject of the equation gives Q equal IT. So let's replace Q by its expression IT now, where I is current and T is time. Now replacing Q by its expression IT gives W over ITI. which simplifies to W over I squared T. Now students, in this expression, W is energy and its SI base units are kilogram meter squared per second squared. I is current and its SI base unit is ampere. So SI base unit of I squared should be ampere squared, and SI base unit of time is second. Students, now we can use this expression to write SI base units for resistance. So SI base units of resistance are equal to SI base units of energy, which are kilogram meter squared per second squared, over SI base unit of current squared, which is ampere squared, times SI base unit of time, which is second. Students, this second in the denominator when shifted to the numerator becomes second inverse, and the whole expression simplifies to kilogram meter squared per second cubed per ampere squared. So these are the SI base units of resistance. Students, our first lesson ends here. In this lesson, we learned first 3 topics of chapter 1, SI based quantities and their units, determining the SI based units of derived quantities, and checking the homogeneity of physical equations. We also did 2 past paper questions on these topics in this lesson. There are 7 more questions on these topics in our workbook. These are the question numbers. Do these questions in the same order as stated here, because they have been arranged in the increasing difficulty level order. But before that, read these topics from my AS Physics notes and learn all the important stuff from there. Students, these notes also contain solutions to these questions and all other questions in the workbook. So if you get stuck on any question or on any part of a question, you may always get help from the notes as well. Students, note that in my notes, additional explanation has also been added in red color to the solutions to the workbook questions. Let me show you a sample solution here. Look students, these equations and other stuff written in red, they serve as additional explanation. You are not required to write this stuff to score the intended marks. The additional explanation has only been added so you can easily understand the solution. I guess that's all for now. To register for my live online AS and A2 physics crash courses, visit my website www.oalevelphysics.com. Thanks for watching the video. Like it if you liked it and do share it with your friends. I'll see you soon in the next lesson. Until then, take care of yourself and everyone around you.